discussion on the ionosphere and space weather, let me tell you two references which I recommend very much to all of you to get access and read. There is a very good book, a monogram on Sun, Earth and Radio. This is written by J.A. Radcliffe, and it's a very good book. Gives almost no mathematics but explains the phenomena starting from Sun, the atmosphere, the ionosphere, their formation, and also the radio propagation through it. So that is one my suggestion. PRL Library has this book. I do not know whether SAC Library has, but they can get it from PRL Library, I'm sure of that. The other thing is on internet, and that is space science comic books. These comic books were originally designed, developed in Japanese by a group of scientists at Japan, and then later the Solar Terrestrial Physics Division of Solar Terrestrial Environment Laboratory at Nagoya University in Japan translated these books in English, and they are available on this is CSSTEAP's. There is a website of it. I'll show you the website also. On that, these are available, and after that, these books have been translated in many international languages, like from Japanese to English, and then to French, Czech language, German, Hindi. The translation of these books in Hindi, I happen to do myself. And while doing the translation, although I had, at that time when I translated, I had worked in the area of space science for about 30 years. But while translating, I learned several new things and very interestingly written books. And then Italian, Russian, Spanish, and some books of these have also been translated in two more Indian languages, Tamil and Urdu. And let me show you the names of these books. This is the website, Space Science Comic Books, that's CSSTEAP. If you search on internet, you will get access to these books in all these languages, including English. And their names are the solar wind. And it not only just tells you what solar wind is, it also tells its origin. It also explains the implication of it and how it really, the whole subject was in a very brief sense and in a very special manner it is described. Similarly, aurora, geomagnetic field, sun-climate relationship, global warming, ozone hole, upper atmosphere, polar regions, and cosmic rays. All these, in fact, relate to space weather program. And these are very small books, just I think 12 to 15 pages each, and has lots of pictures, but explains things in a very lucid manner. And for the talk that I'm going to give today, the most relevant book is this, Upper Atmosphere, because the ionosphere is also called upper atmosphere. So that is this book. I will show the front page and one diagram of this book for your interest. The front page of this is like this. What is the upper atmosphere? And the artwork was done by Hanon, a Japanese artist, and the translation to English was done by Nada and Kamida of Nagoya University in Japan, and they are available on the website. And then from there, people translated in other languages. And one of the diagram which is there in this tells you the structure of atmosphere, which I will discuss in detail in today's talk. That is like the sky above us can be divided into several layers, and these are the layers: thermosphere, and in that there is ionosphere, there is mesosphere, stratosphere, and troposphere, and then what all takes place there, that also is. So it's a very interestingly described in this book. So I suggest you to get access to this and use them as and when possible. And they are freely available. You can even download freely from there. In fact, the translated book in Hindi were have been were printed by ISRO, some I think around few thousand copy or so, and distributed to schools and colleges, university library, and after that many others obtained copy of those and distributed in colleges. So they are very interesting books. Now let us begin the discussion on the topic that I want to share with you today, and that is let us begin with the spectrum of the sun. I'm sure you had a course on sun already, but if not, I will sort of recapitulate that. As you all know, sun that we see is in visible light. We can see all the time. If the clouds are not there, and that is this range. These colors shown here are the visible light that we get from the sun. But sun not only just gives, though this is the maximum energy from the sun comes in this band, that is about 43%. But the rest 57% also comes either on the longer wavelength side and some on the higher wavelength side. This higher wavelength side, the energy that we get from the sun is only 7 to 8%. It's not very large, but it plays very, very important role in formation of ionosphere and ionospheric layers, and also in this region, this X-ray especially is the one which in fact disturbs the ionosphere severely sometimes, and most of the time it remains quiet, but there are disturbances on the sun, active regions, some activities take place there, and with that the X-ray disturbs. I'll discuss some of these points. So though this energy is only 7% of the total energy that we get from the sun, but it plays very important role in our life, especially the communication, the satellite communication, the radio communication, and all these, including the formation of the layers that we have. This part is also important because in this, the first part is the infrared radiation, which gives us mostly the heat that we get, or the warmth that we have on the earth is mostly comes through this radiation. Then it also gives microwave emission. It also gives very low frequency, up to very low frequency. The wavelength is written here. See, like here, this range of wavelength is about 400 to 700 nanometer. So that is the optical signal. And this is lower than 400 nanometer, up to few nanometers. That is ultraviolet and X-rays and gamma rays. And also some particles come from the sun. I will discuss those things. And on this side is the up to here, this is 1 millimeter, then 1 meter, 1 kilometer, and 100 kilometer. So it's a very vast spectrum that we have that comes from the sun, and it impacts us. The part that we have in this, in fact, becomes a noise for several transmitting systems that we have on the earth, including microwave and the radio waves, because these are the waves that are used mostly in the communication. And whenever as you see here, that in the microwave and in the radio, the intensity is lower, but it is that low energy also is significant, and it becomes more significant when there is a activity on the sun, and at that time the disturbance in the TV signal, the radio signal very, very important by this reason. Now we go to discuss about what all possible effects that this electromagnetic radiation source, in our case it is sun, but any source if we have up in the sky will have several effects on us. Like some radiation can come directly to us, and the one that comes directly to us is mostly uh, the light signal from the sun. We see sun, and we get during the day all our houses get lighted, all our lamps everywhere, in the entire this thing we in the entire region, the light is abundant just because of that. It also gives, as I mentioned, infrared, and some part of that infrared gets absorbed, or most part gets absorbed, and that warms the earth. And then, because of the warm earth, there is a re-emission. It emits back, and that emission can go up. It can also scatter, and can scatter back from the atmosphere and heats the first few say 100 meter or so of the atmosphere that is there around the sun, and that in fact gives us the feeling of warmness. The heat that we feel is mostly by this re-radiation from the earth. The signal gets scattered in various directions. Some of the scattered signal gets absorbed in the atmosphere. Some, in fact, goes to as high as if there are satellites, especially the remote sensing satellite, the signal goes up there, and then the basic uses by to study the on a larger scale the Earth's property or Earth's that we have around by remote sensing technique. This is the part that used there, and some get scattered. From this source, there is also scattering by clouds, by particles, and that more or less the signal gets lost there. It also, in fact, remains there. And then there is a absorption along the, this is the one that really creates the ionosphere or the layers of ionosphere that we will consider further. So now in this picture, I have shown one very interesting thing, which is here, that if we measure the temperature of from the earth upward, you see here the temperature is low, and then it remains sort of, this is the region where up to here there is a slight there is a decrease, and then there is an increase, and then it turns back and there is a decrease again, and this is the region that becomes sort of the most cool region of the ionosphere. I will show the bigger picture where you will see this better. But then after that it increases, and this increase is shown by two different curves. One is during solar maximum, and this one is, which is lower, is for solar minimum. Solar maximum and minimum are sort of defined by the number of sunspots that you see on the sun. If you take a picture of the sun, because directly we cannot look at the sun, which is so bright, it will spoil our eyes. But if we use a small telescope, very small telescope, maybe 1 or 2 or up to say 4 inches or so, that gives enough signal from the sun, and you project that on a paper or a screen or put it on the computer, then you will see that in the brightness from the sun is not uniform. There are spots on it. and these are called sunspots. And these sunspots, their number could be, sometimes they can be totally absent. There is almost no spot or very few spots on the sun. But there are times, then gradually this number keeps on becoming more, and in about um, uh, from no sunspot to about becoming very large number of spots, maybe 100 or few hundred sometimes spot. It takes about 5 to 6 years. And once it attains that maximum number of spots, then it starts decreasing. It slowly the number becoming less and less, and again it becomes lower. So that is in about say 11 years. Once from minimum it goes to maximum, comes down to minimum. So that is the 11-year cycle of the sun. In this, when the spots are maximum, then the temperature of the atmosphere, especially the upper part, up to here that it remains more or less same, whether it is solar maxima or minima, but say from something like 150 kilometers upward, which is the large part is the ionosphere, there the temperature during solar maxima is more and solar minima is less. And this produces several effects of which I will discuss later on the ionosphere. For the formation of ionosphere, we have these radiations. These are the radiations like this. This is visible. It comes all the way to us, and we see and we get light. On this side, there is this ultraviolet, middle ultraviolet, far ultraviolet, and extreme ultraviolet, and X-rays. And X-rays also are divided into two: the soft X-ray and the hard X-ray. So these are the regions that or these are the spectra, the part of the spectra which becomes important for us for the formation of ionosphere and all the activities that we see in the ionosphere. Another important thing that we also should see here is the distribution of, mostly on the ground. If we take the sample of the air, it has oxygen and nitrogen. They are about, major is nitrogen, oxygen is about 1/3 or less than that, and there is some part of like carbon dioxide. Those are called minor gases. Their number is very small, but they also play a very important role in the lower part of the atmosphere. And as we go up, some part gets ionized. So here, 3 species are shown: O2, that is the molecular oxygen, NO2, and O. O becomes very important in this upper part of the ionosphere. This is the ionosphere shown here by this red curve. This is the E region, and this is the F1 and F2 region of the ionosphere. And in this region, the O plays very important role, and that remains very high. Now let us discuss in more detail the what happens in the region of interest, that is the ionosphere. Ionosphere is the part where, like on the near the surface, there is hardly any charge. That sometimes the air that we have around us, where there can be very small charge because of the cosmic rays sometimes, but not the amount that we can feel, or even the radio signal or any signal is used in the communication can sort of decipher that effect. So that is almost negligible. But as we go up, say a height of about 70-80 kilometers above the earth, and that region we call D region of the ionosphere, that is below 100 kilometer. This is the D region, and around 110 kilometer, there is a E region, and then very high. This all is the F layer, ionized F layer. In this we have the ions, the some part of the gas, very initially some very small part of the gas get ionized by the radiation that comes from the sun, mostly sun. Of course, some comes from the stellar space, or from way beyond from the space in the form of cosmic rays, but their contribution is small. Most of the ionization that we have is because of the sun's radiation, and so they get ionized. That is, this part from say here onward is called ionosphere. So it's a very large part of the atmosphere, and it's also called the upper atmosphere. The one important thing of this is that there was a long back a scientist by name Karman, and he sort of estimated for the first time that up to about 100 kilometers, if we take the mass of the atmosphere and take the mass of the atmosphere above, there is a very drastic difference. About 99.9% of the atmosphere of the by mass is present just below 100 kilometers. So this is the most massive part of the atmosphere that is there up to say 100 kilometers. And above that, it's only 0.1% or less. And it becomes even lesser as you go up. Very, very, very low density. So, but this becomes very, the part which has very low mass, the mass content is very low, and that plays a very important role for communication, and also plays important role for several features that we see, like auroras. There are color light is shown here at a height of about 150 or around that. You see auroras, which is also part of the ionosphere, and these auroras are formed basically by the emission by the from the sun. Very energetic charged particle also come along the radiation that I discussed, and because our earth has the magnetic field all around it, so it seals most of these charged particles to enter directly to the earth. But this magnetic field is pushed by the solar wind. So what happens is that near the northern pole and the southern pole, some region gets sort of opened up, because the day side lines of force of the Earth's magnetic field are broken and pushed back. So by pushing back, there becomes a sort of opening on both sides, the north side as well as on the southern side of the magnetosphere, and through that the charged particles can enter the earth. So most of the entry of the charged particle that come from the sun is through those are called polar cusp region, and it enters there, interacts with the local atmosphere and excites them, and they get excited, and then while de-exciting, coming to the normal state, they emit radiation, and that is the radiation, color radiation, that we see in the form of aurora in the northern region as well as in the southern region. Because southern region is not populated, so most of the observation of aurora is from the northern region. And some countries like Canada and some countries of US, which are sort of very close to the polar region, you can see these phenomena very, very nicely. Sometimes when there is a very large activity on the sun in the form of a huge solar flare or coronal mass ejection, at that time lot of material, more material comes from the sun in the form of solar wind, and also the particles associated with that. They come with larger, more velocity and more in number. So then they interact with the Earth's not only the the just in the polar region, but that region gets sort of widen up, because then the pushing of the magnetic field also becomes very large. So more of the cusp region becomes broader, and because they are more energetic, it also disturbs the current in the polar region on both sides. So in such situations, there has been occasion, though rare, but the auroral lights were seen at mid latitude region, say up to 30, 35 or 40-degree latitude in the northern side. Of course, you can also see on the southern side in Australia and those countries, but because the population is less in that region most of the time, so there has not been many observations of that kind. So that is very important part that is played here. We also see, if you look at this night sky, especially at a place where the city light is less, during the day, or not during the day, during night, you see meteors falling. That these are basically objects from the outside, outer part of the sun, which is called the which comes to close to us in the form of comets, and they leave some particles in their orbit, and if they get attracted by the Earth's gravitational force, then they go around the Earth, and when they comes down, and when they reach a height of about 100 120 or so, or even lower, where the density is significantly more, so they can burn out and you can see the comets. Some of the material, if it is very large, it doesn't burn, it also comes down in the form of meteorites. And in this region, in the upper part of the atmosphere, the space shuttle and international space stations, they reside in that region. Now, let us discuss in little more detail the formation of the ionosphere or the ionospheric layers. A lower portion of the atmosphere, as I mentioned, to about say 50-60 kilometers and below, there is hardly any ionization. Sometimes it is because of the cosmic rays, very small electron density is found. But the D region is the first region where there is a significant amount of ionization, and that is done by the hard X-rays which come from the sun, and they become important only not during normal days, but when sun is disturbed, their quantity or the number or the emission becomes very large from the sun, and they increases the ionization in D region by several order of magnitude, and that is the time that the very severe communication problem occurs, that the large part of the transmitted waves from the ground will get absorbed there, and because the communication that we normally have, the ground communication, HF and in the VHF range, is by that there is a transmitter which sends the signal, it goes up and gets reflected from E layer and F layer of the ionosphere, and then is spread to a very large part where you can see this. So that communication becomes very, very difficult at that time, or for some time it can in fact vanish. Though fortunately this doesn't happen too often and does not last very long. The E region is formed by ultraviolet emission, and it ionizes mostly O2 that is molecular oxygen, and also the soft X-ray part of the spectrum ionizes N2. So you have N2 plus and electron, O2 plus and an electron. So this is, but these in this region there is also sort of loss because the density is more. So very soon there is a recombination, and so the ionization does not become very large. But in this region, F1 and F2, where the neutral density is much lower, so there the recombination, there is ionization by the radiation in the ultraviolet region, and also extreme ultraviolet also radiates there, and the main element which gets ionized there is O, and because the density is low, so the collisions are less, so recombination reduces there. So in F region, the ionization stays, and it stays not only during the day when it forms, it remains during the night. So the F region is sort of 24 hours, it is available in the atmosphere. The E region, almost immediately after sunset, it disappears. But there are occasions when E region also gets sporadic ionization, and it persists sometimes during the day, and during the night, during the day also, along with the E region, there is a sporadic E region which is like irregularities in the atmosphere, and that is the time that it gives more scintillation to radio signals that we get. So this is, and the ionizing radiation and the ionizable constituent of F2 is the same as the F1 layer. This is the kind of profile that you normally get from the sun, that this is the D region, and in E region the density increases and then it decreases because of the recombination, and then F region, again the density increases, it reaches to a very high density which is called Nmax, and the height of where it happens is called the height of the maximum height of the F layer, and then it decreases. So, and this part of the ionosphere is called, from the above the maximum electron density, is called the top side ionosphere. This is bottom side ionosphere. When we discuss about the measurements, the ground-based method, using ground-based method, you can study about up to about this region, up to the maximum electron density region, and the top side is studied by putting instruments in the satellite and sending waves from there. So so combining both these, you can derive the profile of this type. Now we go to the measurement techniques of the ionosphere, and there are several techniques. Initially, there were radio propagation experiments. Mostly, these were all from the ground. That ionosound, the absorption measurement, how much the radio waves get absorbed in the ionosphere, ionospheric drift, partial reflection, and there are radars like this coherent backscatter radar, which is there in Galanki in southern part of India, and there are several other radars, coherent as well as incoherent radars, which measures most of the parameters of the atmosphere and also the ionosphere. It can measure the density, it can measure the temperature, it can also measure the velocity. So it gives very vast range of information. These experiments gave the initial information, and like I mentioned, that the tops up above where the electron density is maximum, the radio waves from the ground cannot reach that part. So that then that is either sounded by rockets or putting probes in the orbiting satellite, that you put a transmitter there and it goes down and then it gets back reflected back to the satellite and gives you the information of density, electron density in that region. So, and then there are these radio beacon satellites like GPS satellites and many geocitizen satellite by which large part of the atmosphere, its irregularities in the upper atmosphere, velocity, direction, phase shift, group delay, all that can be studied using this. So some of these in which I am little more familiar, I'll discuss, and I also happen to do some little work in these. I will discuss those in some more detail. So ionosound, the basic principle of ionosound is that it has one transmitter. You have a very powerful transmitter and transmit a radio pulse. You pulse is of few microsecond width, and once you transmit it upward, it goes to up in the upper atmosphere, and wherever the frequency of this wave that we have sent from the ground almost becomes equal to the plasma frequency in the ionosphere, it gets reflected there, because the ionosphere acts as a refractive medium for the radio waves. For optical waves, it is more or less, it doesn't affect, but to radio waves, it affects. So it becomes it reflects back, and then the reflected back signal is received almost at the same site, and that is the one it is then recorded as a function of, because you change the frequency of the transmitter and then keep on receiving and then display it in the form of a thing called ionogram, which looks something like this. That this is the frequency starting from 1 megahertz to about 20 megahertz, 19 or 20 megahertz, and then this is the height in the atmosphere, in the upper atmosphere or the ionosphere, and these are the places where from you get the signal. This is like E region, so you can get the maximum FOE, that is called the critical frequency of the E region, can be derived from here. You can also derive the height of E region, at what height it is. To derive height, you use this formula, that you measure the time delay from the transmission to the received back, how much time it has taken, multiply that by velocity of light, divide by 2, that gives you the height. And same way, you can also derive this part is F1, this is whole is F region, but it is divided into 2. This is F1 region, this is F2 region. So here also you can get the height of F1, F2 here. You can also determine the maximum frequency which can be reflected by the F region, and that also sets the sort of the height up to which there is this bottom side ionosphere, the upper is the top side ionosphere. So these parameters can be derived. And as I mentioned, that to sound or to learn about the top side of the ionosphere, there are top side sounders in which the transmitter is put in a satellite, and then it can sense the top side of the ionosphere and also aurora. They are discussed in these. And the density, again, there also, whatever frequency gets reflected back, you can derive the electron density by using this formula. Of course, this formula is sort of common, same applies to the ground measurements also. The carrier frequency is square, you multiply that by 10 to the power 4, and also this constant 1.4 gives you the density. So this way, the entire density profile of the bottom side ionosphere and the top side ionosphere can be derived. The another interesting experiment is the drift measurement. This also works almost on the similar line as the ionosound, but with a slight difference. That in this, there is a transmitter which transmits the signal upward, and the signal gets reflected back, and you receive that signal. But here, we don't change the frequency. The transmitter frequency remains same. So as a function of time, if you record the signal strength, it gives you a curve of this type. This is called fading. That without changing the frequency of the transmitter, you keep on receiving the signal that comes back from the ionosphere. So you get this maximum from here, increase, decrease, increase, decrease. So there are several maximas that you will record. There are several minimas. This difference between maxima, minima, these will depend on the kind of absorption, the scattering that takes place. It's basically the presence of irregularities in the E region and F region of the ionosphere, which manifests itself in the form of this kind of curve. And if you use say lower frequency, let's say about 2.5 megahertz, that those frequencies get reflected from E region. If you increase the frequency to F, say 4 or 5 megahertz, then the E region is not able to, as we have seen in the ionogram, that the frequencies above about 2.5 gets reflected from the F region, and then you get the similar curve. May not be exactly same spacing and same peak and dips, but a similar signal power curve you will get from that. Now, if you, instead of having just one station, suppose you locate 3 stations, which I show in the next figure here, that I have, there is one transmitter which sends signal up in the atmosphere, in the ionosphere, and to receive, I had put 3 antennas, A, B, and C, and receive at all these 3 sites. So when I receive at all these 3 sites, the train of maxima, minima that you have seen in the last picture, that will have all these maxima, minima. If suppose it is moving in this direction, then a maxima at B will be seen first, and then it will later on it will be seen at A, and later on it will be seen at third station C, depending on the direction, of course. So if it is moving in this direction, then this is the case. And this time delay from the displacement of these maxima, minima, you can record this intensity curve at these 3 places and then compare them. And while comparing from several of those maxima or minima, wherever the comparison is good, you can sort of calculate how much is the shift. So that gives you the time of that the wave train, this or the fading train takes from A to B, this is the distance, and from A to B to C. So thereby, and so with this you can calculate how much is the velocity and also the direction in which it is moving. And you can in fact, by counting the number of fades and the velocity, you can also estimate roughly the size and its variation as a function of time. So these 3 parameters and their temporal variation, partial variation, can be studied by this method. This method was developed by Mitra, S.N. Mitra, in 1949, and has been used world over by several systems. In fact, not only in the ionosphere, it is also the same method is used in to study the solar wind by the interplanetary scintillation method. So there also you put 3 or 4 stations and observe a radio galaxy, and the signal from that galaxy will pass through the interplanetary medium and will give you similar kind of fading, though the fading rate there will be much different than the fading rate that I have shown during of the last slide. But then in that also you can sort of calculate the velocity, and it is being used even today. Then some of the results of this method I show here, which also led to a very important discovery of electrojet and things that we will discuss slightly later. That if you these are the measurements done by PRL group at um, Trivandrum. They had the first drift station there, and these are the direction for E region and F region. For E region, 2.2 megahertz is used. For F region, 4.7 megahertz is used. And the interesting part that you see here is that the um, most of the time, the direction is 270 degree, and another time it is much lower. About 75% of the time, the direction is 270 degree, which means that that is the ionization is moving westward, and for E region as well as in the F region. Of course, there are some peaks at say 90 degree. This one, which are very rarely seen, but that in fact becomes another interesting thing. This is part of the electrojet, and this becomes part of the counter electrojet. We may discuss some part of it later on. The velocity has a larger distribution. This is the speed of the E region drift, F region drift, and it has a spread. And most of these are in the range of few hundred meters per second. Here, F region is slightly higher, but there is a spread in both these. And in fact, each there are two curves shown. One is by similar fade method, and the other one is by cross correlation method. Cross correlation method is a computational intensive, but it's little more accurate, and that's why the two curves are slightly different, but both gives a reasonably good observation. There was a drift measurement at Ahmedabad in PRL, and this was my first research project that I had in PRL, where we had a transmitter which can transmit at 2.6 megahertz, and by doing that we study E region of the ionosphere, and 4 megahertz transmitter will give you the study of F region. But here the direction and also the velocity is quite well spread, because Trivandrum is a station in the equatorial part, but almost very close to the dip equator, where the magnetic field is horizontal. So that ionosphere there behaves differently than the ionosphere at low latitude and mid latitude and higher latitude. So this, and the velocity also is much lower here. It's about 400 to 40 to 100 meter, whereas there it is 100 to 300-400 in large part of the time. And the direction sort of keeps sometimes northwest, southeast, and all sorts of. And there is no very marked directionality in the motion of the ionosphere here, but it has irregularities. You can determine the size of the irregularities and all that. This is the picture of MST radar, which is there at Gelenki, and it has a antenna array of 32 by 32, which is very large area. I think during your scientific visit, you may go and see this station, a very interesting one, and it measures the lower atmosphere and higher upper atmosphere as well. Here is an example. It shows the zonal wind and the meridional. Zonal wind is like east-west motion of the atmosphere, and the meridional is the component which is sort of north-south. And here the radar measurement, which is shown by blue, is compared with GPS, and both gives very interesting similar results. So, and a lot of research work is being done at this station. And there are other MST incoherent. The radar that is there at Gedenki is a coherent radar. There are incoherent radars which it becomes more powerful. The picture that you see here is of IceCat, which operates at 931 megahertz higher frequency, and at Arecibo, which is basically a non-moving dish created in the hill region of the USA, and it remains fixed. But then, because Earth uh, uh, rotates around its axis, so it stays different part all the time. So this also is used for atmosphere. These diseases are also used for other studies of the astronomy. Now we go to another interesting technique, the measurement of total electron content of the ionosphere, which is the most effective or most part that need to be considered for navigation or like GPS positioning, etc., or in any navigational positioning system that you have. And that is because Earth's ionosphere it has a ionized layer. It has electrons in abundance, and they are present from say 100 kilometer and all above, and their number keeps on varying, especially as well as temporally, as a function of one place to the other place, as a function of at a given place, as a function of time, it varies. So determination of how much is the total electron content is very, very important. And the refraction and diffraction through these ionosphere of the signals that come from the satellite to the receiver on the, like when we use GPS or Navic for navigation. This the study or the model of TEC is used there, and this TEC is measured by several techniques. One of the most interesting technique is the Faraday rotation. That is that if you on the satellite, if you have a radio wave transmitter which is linearly polarized, which transmits linearly polarized wave, and when this passes through ionized medium with a magnetic field present, the plane the polarization plane will rotate, and that the amount of rotation is relatable to the wave frequency and also the number of the density all along the path h1 to h2. It is integrated, that is from say something like 100 kilometer to 500 kilometers, and then density at different places. And once you integrate, then you get the total. This gives you the total intensity, and you use the magnetic field of the Earth, a model, how it changes. There is a matrix which is put into this equation, and then this angle, that is the angle between the radio wave and line of sight. So using that, you can determine the total electron content. And there has been several experiments in India and abroad, several places, but I will discuss very few of these. One of ATS-6. This ATS-6 was a geostationary satellite, and it was brought over India for almost a year in 1975-76, and they did lots of experiments on several places in India. And this graph that I'm showing is of Uti or Uttarakhand in the Nilgiri Hills, and the stop curve gives the variation of total electron content. This is the total electron content. This is the local time there. This is local noon, 12 o'clock, when sun is at the highest elevation. And you can see that in the morning hours, say at about 5:30 or so, the total electron content increases and it starts increasing and keeps on increasing up to say about 2 o'clock in the afternoon, and then it drops, and then there is sometimes there is little variation. This is compared. This is the equatorial measurement. This compared with the previous years when the satellite was over America, because this was a joint project of India and America. That is why this American satellite was moved over to India, and here it is compared with Boulder. Boulder is a sort of a mid-latitude station, and there there is a increase in the total electron content up to noon, and then there is a decrease. But this, as you see here, this is much lower. It's about 25, and this is more than 55 or almost 60. So it's almost double. So the ionization, the total content at the equatorial region, and they are around the same time of the year, October. In fact, Boulder, because Boulder was the previous year, so they took the median of the measurements of the whole month, and that has this variation. So income, and these are the comparison local, say day-to-day variation that you have in the total electron content of the UT itself in these 3-4 days. So basic concept is that there in the night also there is a total electron content. It decreases in the, up to about on the early morning hours is the least, and then very close to the, because sun rises before when we see sunrise here on the earth at F region, it rises earlier. So you see the total electron content starts rising much earlier than the sunrise on the ground, and it maximizes at about 2 hours and then drops to again the night value. There are lots of measurements of these carried out by physical research laboratory and also other laboratories in Tumba and in India. Several universities took part, and here it shows the diurnal variation as well as day-to-day variation is seen by this width of this green color that you have in these. The interesting thing is this is for winter months. This is for equinoxes, that is March, April, September, and October, and this is summer. The total content is more mostly in the equinox than winter, and the least in summer region in general. And then, of course, these are the normal type measurement when there is a flare or coronal mass ejection or a magnetic storm. At that time, the situation will be different. This is another plot of total electron content measurement at the equator. It shows you the seasonal variation. Here on this axis, we have the local time. This is noon, and this is say midnight. Or then on this axis you have the month: January, February, March, April, May, June, July. So in the middle you have summer, and then the equinox here, 2 months, that is October, November, and also this March, April is the equinox, and on this side you have winter here and winter there. And then this curve shows the line of maximum total electron content, and you can see in summer it is later in the time, in the daytime. It reduces to as it comes to equator, and then to winter is the least. And similarly, this is the lowest total electron content that you observe, and here again it bends slightly when it goes to summer region, and this so the separation of minimum TEC to maximum TEC during summer is highest, and it reduces both sides. So the model that one uses for evaluating GPS delays has to have this sort of variations built in that. Here is the comparison of total electron content with low sunspot and high sunspot. In high sunspot years, see this on this side you have the time. This 0 means midnight, and 24 also midnight, and this is the daytime. Noon is 12 o'clock, and on this axis you have here you have the latitude, and these contours show the value of total electron content in these units. And you see that the total electron content or maximum here is about 50 units. Highest is this is the highest, and this is the lowest total electron content region, right? And this is about 50 here, and in high solar activity period, that is, these are the years 1964-66 is the low sunspot year, where the number of spots were very few, and 67 to 69 is the time when the sunspot numbers were more than 100, I think 150 or so. So, and here the number was much less than 10. So from here, the total electron content is about double. So the total electron content increases from low sunspot to high sunspot, and this increase is more at the latitudes like Ahmedabad. This is the 20. Ahmedabad is at 23, and that's where you see these peaks. And similarly, on the other side, also there is a though here the graph is limited only up to say 10 degree south, but if you see the measurement further, there will be a similar enhancement of the total electron content on the other side of the equator. This is the magnetic equator, where dipole dip latitude is 0. So this is the equator. So almost the same distance on the other side, there will also be the enhancement, and this is called equatorial anomaly. That anomaly, okay, before going to the discussion on anomaly, let me also make a statement here of a very interesting measurements by Deshpande, Watts and Stogie. Deshpande et al. And by this used during that 86 time, there were 6 or 7 stations in India, including one at Uti and all Uttarakhand, and then several up to Patiala. 4 or 5 stations were there. So with that, they made the continuous measurements and compared the magnitude of electrojet strength with the anomaly strength, and they found that there is a very good dependence of the anomaly strength, or they sort of go almost hand in hand with a time delay of about 2 hours. So the 2-hour time delay, the electrojet and the anomaly sort of related. So now we discuss about the anomaly little more, and in this, one of the important thing which plays a very significant role is the conductivity of the ionosphere, which is maximum at E region. If you measure the conductivity, the conductivity is maximum at E region at an altitude of about 100 kilometers, and there is a electric field which sort of developed there, and then there are these electrons, and the electrons can freely move. So that gives rise to a current J, conductivity into the electric field gives you J, and that is plotted here. So there is this current system is present normally in the at a height of about 100 kilometers, 150 kilometers sometimes. So and then you see the center of this is also around the same 30 31 degree, and at the dip equator, at the equator is, and then the direction is different in here and here. So this gives an enhancement of electrojet in this region, and the manifestation of that can be seen by the measurement of magnetic field, especially the H component of the magnetic field based on the ground here. Here, in fact, Government of India has many stations lined up from Ternal Valley, which is the southernmost, and that is in the almost close to zero dip angle or the magnetic equator. And then these are the various stations. Some are there in outside India also, run by the Government of India. And if you combine the observation of these and make a plot, the H component of the magnetic field increases and then decreases. As you go northward, this decrease, there is an increase, but the amount of increase reduces, keep on reducing, and here it becomes very, very low. In fact, there has to, if there was a station, there will be a place where it will be sort of horizontal. That is where that center of that SQ current system lies. And then if you go above that, the three stations are above that region, there you see that it's a decrease in the H component of the magnetic field. So this is the strength of the electrojet. This height, how much is this height, is called the electrojet strength, and the total electron content that you measure and compare that from the equator to onward, that difference is called the ionization anomaly of the ionosphere. So this electrojet is there. In fact, there are three electrojets. One is near the equator in the lower latitude region, and then there are two electrojets, one near the northern polar circle, the other one on the southern polar circle. And these are also called auroral electrojet because that's where you see aurora in that region. And it's at both these places, the main important reason for this electrojet to exist there is basically the fountain effect. That this is for the equator, that there is an electric field which is this direction, east to west, and then there is then the magnetic field is perpendicular to that. The east west is the current, the electric field, and north south is the magnetic field. And this magnetic field for the equator, it becomes almost horizontal. So then the cross of E cross B drift occurs, so that becomes upward. So on the ionization here, there is a force to push it up, and this is pushed up, and then it goes up to, depending on how much is this U, and this will gradually decrease. It will go to some height, and then because there is a magnetic field, from there it will not come back directly, but it will flow along the magnetic lines of force, almost similar to what you have in the water fountain. That if there is the fountain, the water is pushed up, it goes up some height, and then drops on both sides almost symmetrically. Of course, in the ionosphere, it is not so symmetric because the magnetic field is not so symmetric, and there are other dynamical processes that take place. So, but in the ionosphere, by the measurement of electron density in the atmosphere, one can see that these are the region. This is the equator where from the electrons are pushed up and then goes up and then drops back and forms these two regions. This is basically electron density contours. So you see that the density contours at the equator are say 5 in the units of 5.8 or so. But here the electron density is more than 6.2, and here also it is more than. And this is this is the height. The height is this is in the almost the F region, and this also goes up in the F region and then flows back. And so these two regions, say at -18 in this case, they say this also has a variability, and this also around 17-18 degree north. So these becomes the here not only that you have ions produced in the local ionosphere there, but it also gets the electrons that are produced in the equatorial region, and that comes back. And here you see that it is not symmetric like what was shown in the water fountain. It's more or less symmetric, but here it's more towards the north and less. And in some other days it could be the other way as well, depending on the ionospheric conditions. And also it will change from one day to the next day and so on. This also has been seen similar thing by this thermospheric general circulation model, which is developed by Yankor in USA. And here are the three, they show the three examples of this equatorial density anomaly. This is the density increases from green is low and then it increases, red is highest. So this is the highest density region. This is highest here, this is highest here, and this highest here. On this side is that peak is much low, but it does give an indication that there is a and these are at three different longitudes, 285, 300, and this is for 315 degree longitude. And if you go to another latitude, it will probably change that. See, from here to here, this was very strong and this was almost not existent. Here this has been weakened and this side has started developing. Here both are more or less same, and if you go, or in fact this has become stronger. And then later on, if you go to another longitude, it can become similar or the other side will become larger. So there is a lot of change that takes place with the time. And if you, this is also that was by the density measurement, and this is the equatorial anomaly shown by the measurement of total electron content. This is the equator here, and this is the southern latitude up to 80 degree. This is northern latitude up to 80 degree, and this is the curve here shows the measurements of total electron content. That in these latitudes it is lower. This is above the anomaly region, and in the equatorial anomaly there is a sudden rise, very much large here, and this, and then from here this is about 40, and here it is about 140, almost 3 times large. On this side, on the northern side, is weaker, and also at shorter latitudinal difference. Like here, it is at about 23 or 24, whereas here it is at about 10 degree. So the placing is different, but it shows that there is a very clear equatorial anomaly that exists here, that the ionization total electron content is more here, more here. It is not uniform everywhere. This is the magnetic field measurement shown made by the World Org. It's also a model and shows that the magnetic field, the electrostatic strength is more in this region which is called the Indian Ocean region, where the electrojet strength is higher, and it reduces from both sides. It also reduces to the other side as well. Here it's almost absent, and here it again is developed. Now let us have a very short. I think I'm exceeding time, but let me give you quickly some feel of geomagnetic storms, which disturbs the Earth's magnetosphere, and then the disturbance is then communicated to the auroral region in the polar ionosphere, and then from there it travels down to equatorial region, and we get much less effect, but it is there that we do see. The other thing that is also associated is the coronal mass ejection, which also has large amount of plasma, more plasma. It has magnetic field which comes in the form of interplanetary magnetic field, and it affects our the magnetosphere of the Earth. And most of the time, this coronal mass ejection is associated with solar flares and um, storms that take place on the sun. This is how, by measuring the magnetic field on the Earth, you can determine whether it is a disturbed or undisturbed day. Like here, this is a plot of a typical plot shown here, increase, decrease, and all that. And on this side, this is all called, whenever you have this DST measurement, which is a measure of the storm of the Earth's magnetic field, is in this region. It's called high activity region, and if it is in this region, then it is medium, and it is low if it is here. So on a magnetically quiet day, the DST will remain more or less in this region. But this being a disturbed day, it has lots of variation, goes very much low, then comes back, again comes back, so like that. And if once the magnetic field is disturbed, the disturbance lasts for, like here, it began on, say, between on 7th November, and then it became maximum on 8th, but still there was another depression on 10th November, and takes about 5 to 6 days to come back, and thereafter then it will remain in this region. So that will be magnetically quiet period. Of course, most of the time it is magnetic quiet, but whenever this happens, that is the time that we have effects on the communication. And the effect on the ionosphere, it can have two types of effect, basically. It can have positive effect. It can also have negative effect. I'll show you two examples of this. I'll skip this for the want of time. This is the example of positive effect of the storm on the ionosphere. That the ionosphere, the storm started here. This is the DST measurement. The storm starts here, and this decrease, and then it subsides, and then here is the density measurement of the ionosphere. Up to here, the density is, here are two curves. The black curve is the normal day variation, and the blue line and also the thicker line is the disturbed day measurement. So you see that in this region both are same. There is no change. They two remain same. But from here, when the storm occurred, there is an increase, significant increase in blue region. That the disturbed period has higher electron density. and this is explained by downward upwelling of the thermosphere. It comes down, and because of that, the O ionization in the upper part of the atmosphere in the F region gets enhanced. So it is explained here because of that. The other example is the low or the negative effect of this part of the storm. Like here, this is the before the onset of the storm. This is the onset of the storm, and then it deepens and then sort of recovers. So here in this region, both are same, but here the blue is mostly down. Blue, there is a depression. So this is called the negative effect of the storm or the ionospheric storm that has occurred because of the magnetic storms or because of the disturbance that has come from the sun. This is explained here that the negative storm of the ionosphere density has to decrease below the normal level. This is not what you have seen, and it can decrease either by the chemical loss. The loss process gets enhanced, and for loss process to enhance, the O by N2 ratio, because O gets charged and N2 sort of reduces that. So if this ratio decreases, that means O has decreased. So because of that, or N2 has increased, either O has reduced or N2, the concentration of N2 increases because of the upwelling, that the lower part of the atmosphere goes up, so more nitrogen goes up there. So because of that, the loss process will increase, and if the loss process increases, then the density will decrease. Because density at any place that we observe in the ionosphere has three components. One, the production, two, the loss, and third is the transport. Transport, for a shorter period, we can sort of assume it to be same, but the loss, the production and loss process, they compete with each other and produce more or less electron density. This is the classification of solar flares. Maybe this probably you might have seen or studied this in the sun lecture. So we skip this, and I will show you the effect of solar flare. That if normally, as I showed earlier also, that this is the typical ionogram that you see. But if there is a flare which has enhanced ionization in the D region, in the lower part of the ionosphere, the F region does not get any radio signal up to say 9 megahertz. Usually, this is the ionospheric reflection starts say something at around 4 megahertz, or sometimes even lower, 3-4 megahertz onwards. You start seeing the reflection from the F region of the ionosphere. But here you don't see any trace of F region ionogram up to say 9 megahertz. So that means all these radio waves were absorbed by the D region, and these are the frequencies which are used for the communication. So these frequencies, if they are used so they will not propagate, and if they don't propagate, there will be a communication. The similar effect, though not very drastic, but like the flares can increase or decrease the density, there is a shorter period event which takes place in the form of solar eclipse, and the radiation from the sun sort of stopped for sometimes less than a minute or 2 or 3 minutes or so, but it also affects the ionosphere like here, and at density at different height is shown, that there is the eclipse start at this point, and at this eclipse sort of becomes more and more when the moon covers more and more part of the sun. There is a decrease in electron density at several heights. This is 300 kilometer, this 350 kilometer, 400, and this is a 2. So at various height, you see a differential decrease, but decrease is there almost at all height. So, and it lasts for about sometimes for about few hours, because though this is the time written here is 8, this is about 1 hour, this is about 2 hours. So though the eclipse is only for a shorter period, maybe 1 or 2 minutes, but its effect on the ionosphere can last for about hour or so. I think this was my last slide. So I thank you all for listening me so patiently. And in this talk, I have used material from books, research papers. Some references I have given on the slide, but some are not there. I'm thankful to all those authors, and some material is taken from the internet. I'm deeply thankful to all these educational resources. Thank you very much.